spherically symmetric. The radial part is of this form. So the part that involves the R in your Laplacian is of this form, and it's non-trivial. If I do this course, I'll probably use the Schaum, SCHAUM series, which are quite excellent, and they have a really good book on vector calculus in the Schaum publisher series. And deriving this kind of stuff is well towards the end of the book, and the book is quite thick. It's about this thick, right? So there's a lot of stuff. So that would be our whole course. Anyway, the radius, the R part of the Laplacian is of this form. And since we're assuming V is radially symmetric, we can sort of forget about the theta phi part, and you're then able to rewrite, and I'm glossing over things a bit here, especially for those of you who have not done vector calculus, which is undergrad stuff. I think second, third year undergrad. So you can rewrite your STI, your Schrödinger time-independent equation, for the R part of it. The U of R part of it. You'll get this. So here's your del squared, the R part of it, of your del squared here. Well, of course you've got your minus h bar squared over 2n. That's just typical of your Schrödinger equation. What happened to the R squared? Oh, well, I'm a little confused. It seems to be missing an R squared here. Well, okay. Just assume. Let me just check I haven't made a mistake from the. No, that's what it is. Right? So the Schrödinger equation, you just have to accept it then, I guess. The Schrödinger equation then, with this, the R part of the Laplacian, takes this form. All right? Now it's a bit of a mouthful. So let's simplify it by substitution of variables, translating variables. So instead of R, let's talk about, I guess this character is rho, RHO, Greek letter, I think. So define rho to be just alpha R, and alpha squared is this stuff. We've done that before. And another new variable here, lambda, which is defined. We should have 3 bars here by definition. So lambda is 2me over e squared divided by 4 pi beta 0 whatever alpha h bar squared. Right? And I ask you now the next step to do for homework. Plugging in these 3 values here allows you to simplify this Schrödinger equation to the following form. Okay? So do that for homework. Right? Now, as usual, at this stage, you're solving the Schrödinger equation becomes solving a differential equation, a DE. So now we have to solve this equation. So this is the Schrödinger equation, the R part. Well, sort of. I mean, it's the rho part, the R part. They're proportional. So solving the Schrödinger equation now boils down to solving this DE, this differential equation. Now, we can use similar techniques to earlier lecture or so when talking about the simple harmonic oscillator. So the technique used here you'll be somewhat familiar with because it's similar to the simple harmonic oscillator analysis that we did. Right? So as R goes to infinity, you expect your u to go to 0. So for large rho, or large R, they're equivalent, right? So for large rho, you can actually find that u, your eigenfunction here, hold on, no, just it's your wave function, is that this is the solution for your wave function, the exponential minus rho over 2. That's, do that, I wrote here, homework, do that also for homework. So substitute in e to the minus rho over 2 into this, and given that u goes to nothing at large R, you'll find, and this, do prove this for homework, you'll find that this is a solution to this problem at large rho, when rho's large. When rho's large, certain terms will drop out and so forth. Okay? Alright? Now, as before, we sort of guess a trial solution, a trial function. That's remember the word Ansatz we did before, German word. To put in German, setzen, to put, Satz like a place, to like to put on. Well, anyway, the meaning of Ansatz is like in this context is a trial solution, something, an attempt, a guess basically, well, an informed guess. So let's assume for our Ansatz a probable solution for u is this form times some polynomial. That's a polynomial in this case in rho, and that's similar. This product of an exponential term times a polynomial. That's similar to the simple harmonic oscillator work that we did earlier lecture. Okay, so as an Ansatz, as a trial solution, like a guess, we'll try this product. So a polynomial in rho, f, times an exponential minus rho over 2. Okay, so now so that places restrictions on your f. What is this polynomial? So put this product f exponential. So put that in here, u and u. Now differentiate all this stuff, and you'll now get a new equation involving the f, right? And here it is. Again, homework. So quite a bit of homework this session. So if you're following this stuff seriously, and you genuinely want to become a mathematical physicist, or at least get the knowledge of a mathematical physicist, then, as the Americans say, no pain, no gain. Right? You have to work. And as I get more and more into this stuff, I'll be assuming a higher and higher intelligence level of my students, followers, whatever, and the expectation that you will be working, right? You have to sit down with pad and pencil, and you have to really start calculating. Okay, so plug in the f exponential into this and show for homework that you get this expression, right? So d squared f d rho squared blah blah blah. Okay, you get this equation. This again a differential equation, and from this we can start making various deductions. Now I've labeled this equation just simply cross star multiply x, or x star. I'll call it x star, right? So this equation labeled by x star. Now we're assuming that f, and that's the Ansatz, that's the guess, the proposal, the trial solution. We're assuming that big F here is a polynomial, okay, in rho, polynomial in rho. So it'll be of the form, well, let's say the highest power of your rho in the polynomial is k, little k. So your F would be of the form rho to power k minus, or say plus a rho to power k minus 1 plus b rho to power k minus 2 dot dot dot. Right? So let's assume the highest power is k, little k. So in your polynomial, so you've got rho to the k. Okay, so that means due to this rho to the k in the polynomial, on the left-hand side, because you're differentiating it twice, you differentiate this rho to the k twice, so that's where this term comes from. Okay, so you get k minus 1, and